Hello, George Romanich here. Imagine you're an Ant-Man and you can scale down to the size of atoms in the air in your room. And imagine you catch a ride on one of these atoms that is zipping across the room. What would be average speed of other atoms that are moving relative to you? That's what we are going to explore in today's video, and that's called mean relative speed. Today we are going to look into the case if all atoms are of the same kind. But later we might generalize this to atoms of different kinds. This is a beautiful exploration, and you will see that mean relative speeds are of course higher than mean speeds looked at from the so-called laboratory reference frame. Mean speed that we calculated in previous videos was speed with respect to a reference system that is not moving. And that's called laboratory reference frame. But if you are catching ride on one of these atoms, other atoms are moving relative to you, and your relative speed is higher. How higher and how do we get to this result will be explored right now. Let us look into a case when we have many particles in a gas like this, and we saw, and now numerous times, that these particles are moving in any given direction and they have different values of velocities. So maybe this one has this intensity of velocity moving in that direction. Maybe this one is standing still. This one is going in that direction, this one here. So it's a chaotic environment described by our beautiful theory of kinetic theory of gases. So the question is, if you can scale yourself to the size of these atoms and you catch a ride on this atom, what is the speed of other atoms in the gas that you would perceive if you can be Ant-Man and be of this size? Well, if we look into these two atoms that I just described, and I said this one doesn't move, let's assume, has zero speed. If I zoom in, I will say this atom, let's make it bigger, call it atom 1, is moving in this direction. Let's assume that's that direction. And this atom over here is not moving. So this one has speed v1, and the speed of atom 2 is 0. So what is perceived speed if you are catching ride on atom 1? That's called relative speed. So relative speed from the point of view of atom 1, that's what this index means, is v2 minus v1, but v2 is 0, so you get result negative v1. And that makes sense because if you are riding on this particle, you don't have a feeling of motion. What you actually think is that you are standing still and this atom is moving towards you with the velocity negative v1. What is relative velocity from the point of view of particle 2? Well, that's simple. That's v1 minus v2, but v2 is 0, so you just get nice v1. And that makes sense because this one is not moving, so it just perceives that particle 1 is moving with the velocity v1. Where velocities v1 and v2 equals 0 are velocities that we observe from this laboratory reference frame. Of course, we can look into more interesting case when we don't have particle 2 not moving. Let's look into these two particles. Let's say this particle 2 is moving like so. And now, if I zoom in these two cases, situation gets a little bit more complicated, but more interesting. So particle 1 is moving like so, with velocity v1, and particle 2, I plotted it here, has smaller velocity like this, v2. Now, v relative from the point of view of particle 1 is once again v2 minus v1. But now we have to do vector subtraction, and I have video on that. The way you do it is you position vector v2, in this case like it is here, and now I connect tips of these vectors. This is vector v1, and I connect tip to this vector v2, and notice that this is v relative from the point of view of particle 1. Subtracting vectors is sometimes tricky, so it's easier to rearrange this formula and say that v2 needs to be v relative 1 plus v1, and that makes sense, because v relative 1 plus v1 will give me v2. Now if I look into this same situation, but from the point of view of particle 2, relative speeds are v1 minus v2, and I will get the same result, notice, but just the vector will point in this direction. So this is v relative from the point of view of particle 2. What I wanted to demonstrate is that in both cases, this trivial case, as well as this non-trivial case where we have to deal with vectors, intensity of relative speeds is the same, only direction changes, which is indicated here with minus and here with opposite direction of these vectors. So to find relative speed between two atoms, I really don't care about direction. I only care about speed. And we are interested here in particular, of course, in mean relative speed, not any given, but mean, averaged over all these particles. To get that, I will take this formula and square it. So I will get that v relative squared, okay, let me put vector, but of course the result will be scalar. Now you might say, but why are you squaring this one? Why not that one? Well, I just demonstrate it doesn't matter, because intensity is the same. Is equal, now squaring this will give me v1 squared plus v2 squared minus 2 v1 dot v2. Now I will carry out averaging operation of this expression, and I want average relative speed, so it makes sense to take average. So I will get that average v relative squared is equal average of v1 squared plus v2 squared averaged and minus 2 average of v1 dot product v2. But what is average of v1 squared and average of v2 squared? Well, mean speed of all particles is the same. So average of v1 squared is equal average of v2 squared, and that's just some mean square speed of all atoms in this gas. But how about this term over here? Well, this term I demonstrated in my video on temperature of a gas must be 0, because there is no preferred direction of motion in a gas that is in thermal equilibrium. These two particles, you see, will maybe collide over here and then bounce off in some direction. But I am not interested in these two in particular. I am interested in average over all collisions in this gas. And because motion is chaotic, as I indicated here, on average there is no preferred direction of collision. So on average this term has to be 0. In other way, what we discussed in my video on temperature of a gas, we could say that there is no correlation between two velocity vectors on average. So putting everything together, we can see that square of relative velocity averaged is equal this plus this, that's 2 times mean square speed. Now it is very tempting to take square root of this equation, and if you do that, interestingly, you will get correct result. But you will get correct result for wrong reasons. Because it is not correct to just take square root of this and cancel square and root, because averaging process comes after squaring process. So you need to demonstrate that in this case, it is safe to take square root of both sides and get the right result. And that's what I am going to do now. We know from my video on root mean square speed that mean square speed, this is equal 3 times k times t divided by m. We derive this explicitly where k is Boltzmann constant, t is absolute temperature of the gas, and m is mass of atom. Similarly, from my video on mean speed of atoms in a gas, we saw that that is equal 8 kt divided by pi m. Now let me square this equation to get that mean v squared is equal 8 kt divided by pi m. And now I will divide this expression with this expression to get that mean square speed divided by the square of mean speed is equal, if you divide these two, you will see that temperatures cancel, you will see that Boltzmann constant cancels, you will see that masses cancel, so you will get result 3 pi over 8. And this is actually a very beautiful result that tells you that the relationship between mean square speed and square of mean speed is a constant that does not depend on temperature, pressure, mass, or on anything. So you can see from here that mean square speed is simply equal 3 pi divided by 8 times the square of the mean speed. And now when I demonstrated that there is this relationship between mean square speed and square of mean speed, I can apply that relationship here and get that 3 pi divided by 8 of square of mean relative speed is equal to, and that's this 2, times 3 pi over 8 square of mean speed. These factors cancel, and now it is safe to take square root to get our final result that mean relative speed is simply equal square root of 2 mean speed. Absolutely beautiful result. And of course, I already know what mean speed is, so I can write here finally that mean relative speed is therefore equal 2 times 8 is 16, so I will get square root of 16 kt divided by pi m. And this is relative velocity between atoms of same kind in a gas that we described here. As in previous videos, I already prepared a nice table that shows you calculations of relative speed for gases that make up air plus radon as an interesting gas. And you can see that relative speed is of course always higher than mean speed. All these other speeds were already explicitly derived and discussed in my previous videos. In several previous videos, we explored some of the most important characteristic velocities in an ideal gas, such as air in our rooms. So we looked into mean speed of atoms in a gas, mode speed or the most likely speed of atoms, median speed, root mean square speed, and today mean relative speed of atoms moving relative to each other. Now we can move forward and investigate mean free path of atoms, which is average distance any atom travels before colliding with another atom. We'll see that order of magnitudes are again amazing, 10 to power negative 7 meters or so. And that's because numbers are so large in terms of the concentration of atoms and molecules in the environment, in the atmosphere around us, that the numbers that we get are either very small or very large to the point that our brains cannot comprehend that. And that's why we have kinetic theory of gases and Maxwell-Boltzmann distribution and Boltzmann distribution of energies and all these derived quantities from these distributions that help us to visualize something that our eyes cannot see. Until next video, goodbye.